Hello, we're going to be discussing running water, streams, and rivers in this lecture. This is chapter 12 in the book. We know that running water, which is a part of the hydrosphere, does considerable geological work in the sense of erosion and movement of material around the planet. So water is continuously cycled from the oceans to land and back to the oceans, and it's gravity that actually does most of the work when we think about water moving stuff. It's gravity that pulls the water down from high elevation to lower elevation until it gets to the sea level, or Death Valley for that matter. But anyway, running water transports large quantities of sediment and deposits sediment in adjacent to braided and meandering rivers and streams. When it's moving material, when that energy in the stream drops to a point where it can no longer move the material, it produces alluvial fans on land or deltas in standing body of water, as would be lakes or the ocean. And then flooding is a natural part of the stream activity that takes place when the channel receives more water than it can handle. We'll talk about the different 10, 100, and 1,000-year floods. Talk about rivers and streams and how they continuously adjust to changes. Water follows the path of least resistance, just like energy does. If you talk about the way lightning moves, that's why we don't stand next to trees and stuff during a lightning storm, because it follows the path of least resistance as well. So the concept of a graded stream is an ideal. We'll talk about why we use that ideal to determine what's going on in the rivers, and then we'll talk about how we use this to look at the condition of the stream. So the hydrosphere, along with the other spheres that we talked about, is the Earth's water. And we know that it is one of the most powerful forces on the planet. So we see on the right, that was a flood in Johnstown, Pennsylvania in 1889, where an 18-meter high wall of water destroyed Johnstown and killed at least 2,200 people, so it took out the whole town. And then we have the monsoon rains that we're familiar with, and this is in Pakistan, and we get flooding like that. It's pretty dramatic. And consider 20% of Pakistan was covered when these monsoon rains hit. They're quite dramatic in how they change the surface of the planet. But we know that Earth has an abundant supply of liquid water, while we know Mercury, Venus, and Mars, all of these other rocky planets, had water on them at some time and have a similar history. But right now, we're the only ones that currently has liquid water. We know that we have the Mars Surveyor or the Mars robots up there looking for water, see if we know that it was there in the past, and we think there is some water there today, but not as much as what used to be there. We don't know what happened to it. But Mercury is too small, which means it doesn't retain the water, and it's too hot, so it's a vapor. And since its gravity is small enough, it gets stripped away through the solar wind. And then Venus, which has a lot of water, but it also has gone through runaway greenhouse effect, is too hot to have liquid water. And then Mars, which is also on the other side, is too small to retain that or have strong enough gravity to condense the water and have large pools of water. And it's also too cold. And it has moved out to where it is currently in the solar system. It was closer to the sun. And we don't really know why it moved out, but the water went away. We don't know what happened to it. But 71% of the Earth's surface is covered in oceans and seas, and then the atmosphere contains about 4% of the water, and then the rest of the water is either ice or groundwater or rivers. In this slide, we are looking at the hydrological cycle, which means that, or hydrologic cycle, sorry. Water evaporates from the oceans. It gets up to an elevation where the air is too cool to retain that amount of water vapor. It condenses, and then that condensed water produces clouds, and that's what the condensed water is, and it moves over land. And here we have, as these air currents move and they get over mountains, we call this orographic effect, because the density of the air column that's trying to get over the mountains is too dense with the water that is contained in that air column. So in order to get over the mountains, in a sense, as this air column becomes compressed, as it gets over the peaks of these mountains, the water condenses and you get a lot of rain along mountain chains. We call that orographic effect. But the water nonetheless comes out as rain, falls on the mountains as precipitation, and then gets into the streams and then runs through the streams down into either a lake or eventually into the ocean. Most of the water gets into the ground, and it's soil moisture or groundwater. And the lakes and the rivers we see are actually just areas where the land cuts into the groundwater, and so you see the groundwater. That's what a lake is the groundwater, where the elevation of the land cuts down into the groundwater. The hydrologic cycle is the source of all fresh water that we have on land, and it's primarily from the oceans, as I just suggested. But water evaporates from the oceans, plants transpire water, even the water is even evaporating from the land and the lakes and the streams. And so the cycle is going on all the time in many different regions of the world. Eventually the water will return through the process of runoff from these mountains into streams and rivers and return to the ocean. Some water does stay behind if it's frozen in glaciers, but eventually it'll make it through to the oceans. It's just a matter of how long it will take to move through and get to the ocean. So during this process we have fluid flow as it moves towards the ocean. Almost all surface flow is turbulent, just like it says in the slide, and that's capable of erosion and sediment transport. When you look at turbulent flow, the flow lines of the rivers are intertwined in a complex manner, which causes all sorts of eddies and increased rates of movement near the stream bed or next to the side. And when it does this, it picks up material and moves it around. I mean, this is what normally we think of as erosion, but we often don't think about it in a scientific sense. We just look at a stream and go, oh look, it's muddy, and that's a process of erosion right there. There are a few places where mixing doesn't take place because the fluid isn't is producing a laminar flow. That's what we call it, where it's very flat and smooth. I guess would be a good way of saying it's very smooth. This is very rare because we know that the land surface is not smooth, and the water, in a sense, copies what it's running over. And so, in order for the water to have a laminar flow, it has to pass over something like bedrock that doesn't have a lot of other rocky protrusions in it or anything to keep the water running smoothly, which would then of course would reduce erosion, but this is rarely found. And as you see in this picture, we have a stream. It has a lot of mud in it, or a lot of sediment. That's what we would call mud when it's in the stream. And as the sediment moves through, it turns the water kind of a brown color. And this is due to the fact where rainfall or meltwater or something exceeds the ability of the water to infiltrate into the soil. Infiltrate means to be absorbed or move into into the soil and not basically be saturated. The infiltration capacity is affected by the intensity or the duration of either melting heat waves, if it's snow we're talking about, or the amount of runoff from rainfall. And basically once the ground is saturated and can't absorb any more water, it's that water will run off, and that's why we call it runoff. In this slide we are looking at how we determine the rate at which the flow or the movement of the stream will be affected by gravity, in a sense. So we have the gradient, which is basically, think of it as a slope over the extent of the stream. They might be different depending on where you are. If you're at the headwaters, which is the top of the stream, it might be more rapid than you are at the bottom, which would be the tailwaters. Water velocity is different depending on where you are, and then the discharge rate can be different depending on where you are in the stream. So what we do is we actually look at different sections of a stream, and that's what they're showing you here. If you're at the top of the stream and you're measuring gradient velocity and discharge up here, it's going to be different than what it is down here at the bottom. And so a stream's gradient varies greatly from gentle down at the bottom to pretty steep up at the top. And usually at the headwaters is where we have the steepest gradient. There are two ways we can define how water flows over a system. We have sheet flow, which we've already talked about when I talked about erosion. There's sheet erosion, which is one of the fastest ways to erode soil because it goes in sort of a whole sheet and moves as one unit. Or you have channel flow, which is basically runoff that is confined to a channel or a trough or a depression in the ground. And we have a variety of terms that determine the size of the stream. The smallest would be a rill, and then we have a brook, and then we have a creek, and then we have a stream, and we have a river. Those are basically going from the smallest amount of water that's being discharged to the largest amount of water that's being discharged. And gradient velocity and discharge are all related, because the velocity of the water is the measure of the distance the water travels in a given amount of time. And the flow velocity varies downstream at the cross section down at the bottom of the stream, tailwaters, as opposed to the headwaters of the stream. And that's because there's differences in the depth of the stream itself, the slope of the area that you're looking at, and then the roughness of the channel. So think about, I don't know, let me give a good example. If you were to look at the Mississippi, the Arkansas, which is very similar, flows into the Mississippi. If you go to the top of the Arkansas, it starts in Colorado. And so the headwaters of the Arkansas River are very steep, and they're going to be flowing very rapidly. It's going to be filled with boulders and cobblestones and everything else. As you get further down, and that slope or that gradient flattens out, the rate of the water, or how fast it's moving, the velocity slows down. And as it slows down, the roughness of the channel decreases because you're not carrying large enough stuff. Doesn't have enough energy now to carry those larger cobblestones and things down into the channel, so you get sort of a clay or sandy bottom, and now it has much more smooth movement, or that laminar movement we talked about before. Ultimately, when you look at the gradient and the velocity, that's going to give you an idea of what the discharge is going to be, or the volume of water that passes through a given point at any amount at a given time. Discharge generally increases downstream as tributaries input more water into the stream. And so you think of the Mississippi, it has a huge amount of discharge, but it's not moving very rapidly. But that's just because the discharge is dependent upon the size of the stream bed or the channel in which it's flowing. So here in this slide, I show you basically what we've been talking about. We have gradient velocity and discharge, and we're going to calculate a daily discharge for. Let's look at a stream that's 148 meters wide and 2.6 meters deep with a flow velocity of 0.3 meters per second. So the discharge, I've already calculated it out for you, is 115.44 meters cubed per second, or we take 148 meters wide times 2.6 meters deep, and then we multiply that by 0.3 meters per second, which gives us obviously 3 meters, which is meters cubed per second. And if you to put that in perspective, in a single day, you would take this per second, multiply that by 60, multiply that by another 60 to get the minutes, and then multiply that by 24. So you multiply by 60, get discharge per minute. That's 692.4 meters cubed per minute. And we get multiply by 60 again. That's 415,584 meters cubed per hour. And then multiply that by 24, and that ends up being 9,974,016 cubic meters per day. So a relatively small stream. I mean, 148 meters wide, I guess it's pretty wide, but it'd be like, but it's not very deep, 2.6 meters deep. It's a lot of water. I mean, it's a lot of water in a day. And I'm pretty amazed, because if you look at the discharge of the Mississippi, and we know by the time it actually gets down to New Orleans, the Mississippi's been used 6 times. So think of the amount of water that's flowing down. Every bit of water that gets down there, it's been estimated that water's been taken out of the river and returned 6 times. So So what does this running water and erosion and everything have? How are they linked? We have streams and rivers. They possess a potential energy, which means that's the gradient or the gravity, the ability for them to move, or the ability of the water to move. And then the kinetic energy is actually utilizing that potential energy to erode and transport material. And here in this picture, looks like these are ponderosas and lodgepoles in the back. So this is like California or Colorado or somewhere, maybe even Utah. But this stream right here, this is not a very healthy stream bed, because you can see right here it's got a cut bank, but a significantly eroded cut bank, where there should be an even gradation of plants all the way down to the water, maybe a little bit of a rocky pebble material right here at the base. But in fact, this is just eroding and falling in rapidly, which means that this is overgrazed. So this is what you can see. Basically, and this is a process of hydraulic action, or the impact of water on the loose dirt and sediment, that is not held down by plants because they've been eaten by cattle probably. Here we have a picture of abrasion. This would be similar to a sandblaster that we would use on our houses to remove paint, or some area where you want to remove paint, and we just shoot sand using air, compressed air. In this case, it's sand and rocks and stuff that are carried in the water, and they abrade the stream bed, whatever's in the stream bed. In this case, it's rocks, and produce these circular sort of divots in the rock. And this is what it looks like. So running water erodes and transports sediment. In this case, you have a whole bunch of different things going on. You have this dissolved load that is invisible because it's basically all the material that is suspended. Think of this as like sodium chloride and certain salts that stay in solution. And then you have suspended load, which are small particles that stay suspended. Think of like mica, very small pieces of mica that basically fly in the water as it moves. That's suspended material. So we have solution, which is dissolved material, those are the salts. Then you have the micas and things that don't dissolve, they're suspended load. And then you have bed load, which is material that is transported along the bottom. You get traction, where it's just sliding. You get stuff that rolls. And then you get saltation, which is like skipping. That's what it means. It goes, skips here, and then it skips here, and then skips again. That's what saltation means, saltatory activity. But it's moving a large amount of material. Every single stream is, and they will do this in a variety of ways. But if you look at a stream bed, and I'm going to go to the next slide, if you look at a stream bed, you can tell if it's relatively young or old, depending on what it looks like, the size of the sediment that's in there, and what's on the floor of the stream, or the stream bed itself. Here we have a braided stream, which they tend to be relatively either young streams or they're intermittent streams, which means they get intermittent flooding that occurs. In this case, this is like Alaska or somewhere where you have an influx of a lot of water at some point in time, and that's usually due to, I don't know, glaciers or snow melt in the spring. It could also be an area where you get a lot of rainfall. But braided streams have too much sand and gravel to be effectively transported because there's not enough water. So it's the amount of discharge is not sufficient to actually carry all the material. And you get all of these deposited sandbars that divide the main channel into many different smaller channels. The sediment that is deposited is called alluvium. So this is an alluvial deposit. This would be like a sandbar or whatever, and if you get to the bottom where this will move into an open area, you can get an alluvial fan, which we'll talk about in a little bit. But alluvium results from sedimentation that does not continue downstream, and occurs usually during flooding. When I was living in Colorado, or actually I wasn't in Colorado, I was in Utah, and I'd go to Colorado to do research if we had some flash floods. I put that in quote because they're basically just normal rains. We get these huge deposits of clay that would go over the top of the road, and they'd be about a foot deep, and they'd look like this. It'd be like a stream bed and a big mound of clay just sitting in the middle of the road. And I was driving a four-wheel drive truck, but I wouldn't cross that because it'd be so slick, you'd just slide off the road, so you'd have to wait for the earth movers to come and push it out of the way. and it was pretty interesting, but not necessarily fun. I think we have to realize too that when we're talking about how far these deposits move, some of these deposits can start, I don't know, in the Sawtooth Mountains of Idaho and get transported all the way to the ocean. By the time they reach the ocean, they're usually pretty small. It's sand that gets there, sand or clay, something like that, or silt. But that material has moved 2,000 miles by then, or even 5,000 miles, depending on where it started. So continuing with the idea of a braided stream, this is from your book, Braided and Meandering Channels. You have suspended load that is carried in one continuous channel. Here we have a Yazoo stream along the side, but let's just look at this main channel. You have a channel that is cut by the velocity of the water, and the cut bank is where the water accelerates as it comes into the side of the bank and gets pushed across, so that energy is then absorbed by the bottom of the bank right here, and the water will actually shoot out and reach its maximum velocity like an airplane wing in a sense when it reaches the other side, and it can produce another cut bank and come down. And as it does that, everywhere the water slows down as the maximum velocity reaches the other side of the cut bank, you deposit sand, which then we get the point bar or the sandbars that we often talk about. But you actually see on the river. Usually when you see meandering streams, these are older streams or more mature streams, and their deposits are usually mud or silt, and they will have subordinate channel deposit, which means that they have other deposits that are from previous floods or anything else that may be deposited there from other times. And due to the velocity, as I said, being fastest outside of a meander where the erosion cuts into the bank, and we get these cut banks, you can actually cut through these 2 points, and this area out here that is no longer contained within the stream becomes an oxbow lake, like you see here. All these different oxbow lakes here, and that's due to old cut banks that were cut off when the 2 points where the cut bank actually cuts completely through and comes across and enters the channel and cuts off this side sort of meander. I would like to point out that if you look at the inner side of the meander where you're getting this bar formed, if you go to any one of our rivers, including the Grand River, and look at where there's a sandbar, the material at the top up here where the pointer is going to be probably consist of larger material. It'll probably be sand instead of the clay, and as you decrease the velocity of the water, because the decreased energy in the water corresponds to that decrease in velocity, you end up getting finer and finer particulates further on into that sandbar until you get to the end where the velocity is going to be slowest, and it's going to have the finest mud or the finest silt. Also in these all streams you had floodplains. These are areas where the water escapes the natural channel, and as the water escapes the channel, because it slows down, just like in a sandbar, you start depositing material. In this case, you get natural levees developed, and then you get the floodplain and it fills up. And this could be the 10-year floodplain or the 100-year floodplain, depending on how much water is moving through and where you've eroded down into that stream bed. Basically, floodplains are the flat lowland areas that are parallel streams, and they flood regularly, which I find interesting because we tend to build most of or grow food in most of these floodplains because they're very fertile, but they also flood. So when we put in farms, we also build farmhouses, and they're on the floodplain. And if you ever watch the news every spring, the Red River and the rivers up along the border between North Dakota, South Dakota, and Iowa and Minnesota, up in that area, you always get flooding, and they have to sandbag them every year, and that's just natural flooding. It just so happens that some years they're worse than others, but when they're worse than others and they actually are going to come out of the levees we actually have built up, we try to increase the size of those levees by sandbagging, making them higher. The problem with that is as you make the levees higher and higher, you're just sort of staving off the inevitable. It will flood, but when it floods, when the levees are much higher, you're going to reach the floodwaters of a 100-year flood regularly rather than the 10-year flood, depending on what kind of ice wedging we get. But we've already made the levees taller by putting in sandbags and everything else, so that when they actually are overtaken, that there's more water in that stream channel because it's much deeper. So when it erodes through that levee, you end up with worse flooding. And as a result of that flooding and the erosion that comes off, you end up moving these alluvial deposits downstream to the mouth, known as mouth of a stream, known as a delta. So in this case, the delta forms. This could be a lake, it could also be the ocean. But as the water comes off of or out of the channel, the velocity drops because the size of that channel opens up, because you're entering a much larger body of water, and so it slows down. And as it slows down, it starts depositing material, the material that was originally suspended at this velocity, but at the lower energy now it's no longer suspended. And you'll see that it deposits its first on this one layer, and then when it gets to the end where it gets deeper, it starts depositing it off where it really slows down when it gets into the lake. So you have the distributary channel, which is this top layer, and then it gets to the very edge of the lake, slows down dramatically, and you get foreset beds developed. So that sediment comes out here and slows way down and starts putting layers down. Depending on how old the lake is or how much flooding is coming in, these can be of different thicknesses. And then at the very bottom, which is the very finest mud and silt, you get the bottom set beds, which is the stuff that really is very fine. Not all deltas are actually mediated or produced in the same way. When I say mediated, it means they're made in different ways. So here we have, this is probably the Mississippi Delta, where the stream's coming out and deposited just like the picture I just showed you, and you get the top set beds. This is all the stuff material right here. You get the foreset beds along the side. If you were to cut through this, you would see all the different layers. And of course, these are distributary channels that I just talked about. You have the same thing here, because this is the Nile. And the Nile, what happens with the Nile, it's a wave-dominated type of delta where it still has the distributary channels and the top set beds and things like that, but then the waves coming the other action will actually erode and make this nice rounded appearance to the delta. And then you have tidal dominated. This is very familiar to me because I used to live up in Anchorage, and they have all the tidal dominated deltas out there with the rivers coming off from the glaciers. This has actually got to be in the tropics somewhere. I would say somewhere like Thailand or somewhere around there, because it's going to be a big delta coming off the Himalayas. And so because this is all, I can see all this sediment, this purple stuff is sediment from some glaciers or something that contains a lot of this, what we would call glacial milk. So this is a tidal dominated material where it fills up, and then as the tides recede, it's going to pull all of this material from erosion very far up, wherever it is up here, out into the ocean. And it's not going to have the same kind of development that you have the deltas like you saw over here with the Mississippi. But you're still going to have some, if it's a prograde, which means it's a building delta, and this is being deposited faster than it's being eroded, in the sense that the tides are not eroding this back, which they wouldn't. They're pulling sediment out into the ocean. You'd end up getting a very similar set of top set beds, four set beds, and then these bottom set beds are going to be very fine. If you go to an area where there isn't a standing body of water, you get an alluvial fan, and these are quite common. Like I said, those material that got deposited on the road when I was trying to get up to my research plots, that clay and that silt, these are just alluvial fans. They just happen to cover the road, and they have to remove them. What it is like if you had a road that was crossing this, I'm sure there's one along here. Every time this floods, it would cover that road, and they'd have to remove it with a grader. So we have lobate deposits of gravel and sand that are deposited in the lowlands from adjacent highlands. Lobate meaning rounded. And they form usually in deserts, or what they would say in the book, arid and semi-arid regions. And these are regions that have high rates of erosion, but have specific periods of flooding. It's usually in the spring or in areas where you get a massive amount of runoff, or you get torrential rains from a monsoon. In this case, because we have monsoons in Arizona, and when I was in Texas, for example, the Guadalupe River one year, and I think it was 1991, went from the size of the Grand River to bigger than the Mississippi in 2 hours and deposited a whole bunch of material. I always thought it was funny because when I lived in San Antonio, they had dams in San Antonio, like Olmos Basin is a dam, or a basin that's at the end of that basin is a dam, and I always wondered, well, why is that? And it was because we get these massive, they call it flash flood alley, and when they use those dams to slow the water down, but they also get a whole bunch of material deposited, alluvial fan stuff that's deposited in there as well. But as you can see here, we've had multiple flooding events. The geologists put their rock pick in here to show you the size of this material. And then you get a fine layer of sand here. You have another layer where there's bigger rocks, and then a fine layer of sand. So there's been multiple areas where the water was moving relatively fast and probably deposited this fine layer of sand much further down. Because each one of these areas are going to have these top-set beds that are produced by the distributary channel, and this distributary channel is going to be at different velocities as it comes out. There's going to be obviously bigger material at the mouth than there are at the bottom, but the rate and how far these fans develop are dependent upon the amount of water that's coming out. So these lobate deposits might be different depending on how far out you are from the mouth of this alluvial fan or the canyon that produced it. The take-home message for this is deltas and alluvial fans, they're similar. They're basically deposits of alluvium that form at the mouth of a stream or river as the material is deposited because the transport energy drops as the river or stream spreads out into a much larger area and deposits what they call the sediment load or the bed load. Now humans, we're really good at predicting things, and so we can control floods. And we usually build levees and dams. Like I said, the dams in Olmos Basin, or the dam in Olmos Basin, prevents San Antonio from flooding, or not flooding completely, but slows it down so people don't die, but it still floods. And we produce artificial levees where we build high banks, basically on the slide, to prevent water from overtaking things. Like the Red River, like I said, has an artificial levee, but then sometimes the water's too high and we have to, often it's ice damming that creates that backup in the water, but we have to then sandbag along the edge of this levee or these levees to keep the water from going over the top of the levee. But like I said, if you build artificial levees, you're actually creating a system where the flood that's going to occur is going to be a 100-year flood rather than the normal 10-year flood. And it's going to happen more regularly. We also see floodways and flood walls produced. So floodways is where we take water. So obviously this is, I don't know where this is, but you have a bunch of snow back here, and they produce not natural stream, or they channelize the stream and they put in floodways where we expect the water to be diverted when it gets too high. Then you have flood walls. This is a wall. This is probably Europe, where they put gates and other openings so you can get out to the water, but if it's flooding, you close the gate or you keep people from coming into the area, and the water is then stopped from flooding the town. And flooding can be pretty dramatic. I don't know if you guys remember 1993. I'm older than probably a lot of you guys, but in 1993, I purchased a Subaru. Well, actually, I didn't purchase a Subaru. My sister gave me her Subaru, and I thought it was weird that the radiator was all rusted out in a fairly new car. And then I remembered that there were these big floods that we had along the Mississippi and the Ohio River Basin, and there were a whole bunch of cars that were underwater, and they were actually totaled, but then people were selling them again as basically newer cars with low mileage. And so I had to have the radiator replaced and a bunch of other things replaced. It was a great car, but initially it cost me a lot of money to get everything working again. But what you see here is you look at Illinois, Iowa, all these different states, and the total amount of damage resulting from not just agricultural and residential loss, but other things like cars, etc., other manufacturing losses, things like that. So the total of the flood, which was 1993, was $7 billion. That's a lot of money for people to absorb. I mean, that's 7,500 million, right? 7,500 millions that we had to absorb, and it was quite costly. The flood that you just saw is actually contained within a drainage system. And all drainage systems are a little bit different, but in this case is the Wabash River Drainage Basin, which is in Indiana, Ohio, Illinois, and basically all of these different rivers flow into one area. That's right below us in a sense, so that's also part of the Ohio River Basin. And you can see right here, here's the Ohio River Basin, which has a drainage system in it. And there's actually a few areas that if you drive south of Jackson, you'll hit a summit, Summit Township, but it's a summit where they'll tell you the elevation, and basically what you're doing is you're moving from one drainage system into another. And the drainage system that you're going into, well, you're moving from the drainage system that we have in the Grand River that goes from here in Jackson to Lake Michigan. And then the other drainage system, I'm not really sure, maybe it's the Detroit River or something else, will drain into Lake Erie. And it's actually a summit or the high point where the water is moving in different directions, and that's what you can find if you drive south. But each one of these has a different drainage system. So you have the upper Mississippi, the Missouri, the Arkansas, just like I talked about. This beginning of the Arkansas is actually in the Colorado, southern Colorado, and then of course the lower Mississippi drainage system. And these all have different flood stages and different levels at which they will remain fine or flood depending on the amount of water that's moving through them. And the kind of flooding that occurs is dependent obviously on the drainage system. So here we have a dendritic drainage system. This is something you would find usually near the mountains. So you see the areas like the Arkansas River. That's a sort of a dendritic drainage system until it gets into the Arkansas. You have these rectangular systems, which you can see this is a bedded plain, and then these are a lot of areas where you have fractures in the rock, and it's going to follow those fractures, and you get different. This would be an area that is, drawing a blank. I think it's Kansas. I think that's what this looks like. It's also part of the Arkansas drainage system, but the bedrock's a little different. Then you have the trellis system where you have these bedded plain that's turned up, and you can find this in Pennsylvania where you have different ridges of resistant rock, like the areas of the Appalachians, and then they go through, it looks like a trellis, basically, like you would have a trellis with grapes. Then the radial drainage system, which of course is, think of a volcano. And then we have Michigan's drainage system because of glaciation. If you look at, and we will, I'll show you actually when we look at glacial cycles, we'll look at the G-range drainage system of Michigan, which is the Grand River. The point to all these different systems, though, when we talk about drainage system, is they're going to base level because of gravity. So it's the base level will be the lowest level at which streams can erode to, which is sea level. And sea level is basically known as the ultimate base level. We do have areas like the Great Basin, which have lower ultimate base levels, but the ultimate base level, the local base level, the ultimate base level is still the ocean, because if any of those systems were to fill up, they would actually drain into the ocean. And we know that when Lake Bonneville was there, it actually drained out through the northern part of the Great Basin into what is now the Snake River and flowed out into the ocean. So it's still the ultimate base level. It's just right now there's not enough precipitation to fill in that old lake bed. So streams are commonly have local base levels, which are formed by lakes and other areas where you have resistant bedrock or you're cutting through into the water table. And what they're showing you here is you have different kinds of drainage system. So you have a sloping area, so you have erosion at the top, you have a sloping area, you have deposition, you have another erosion area, and then deposition. And if you were to take one of these sections and blow it up, you'd have something called a graded stream, which is a concave upward profile for a stream. And a graded stream is basically a smooth concave longitudinal profile, and you don't really get significant erosion or deposition that takes place along a graded stream channel. The deposition usually occurs in this case it would be the lake or ocean, and erosion takes place, as they show you up here, in areas where you're cutting through these steeper sort of slopes or cliffs where you erode through very rapidly because the water suddenly is moving much more rapid. I think the reason the book shows you this is we're going to move into looking at how valleys evolve or how they are produced. So, evolution of valleys would start here. They're low-lying land areas that are bounded by higher land, such as hills or mountains. We don't really have really large valleys here in Michigan because of our deranged drainage system, but most valleys have a river or stream at the base with tributaries draining into nearby highlands. So in this case you have a bunch of tributaries moving into this stream, and the stream event could be a tributary for another larger stream, but then they're cutting away, eroding down into this area where the land is uneven. So in this slide, I'm sort of taking you through the process. If you start out here, this would be possibly a gully, and then this is a picture from Colorado, where one of my research sites, and what I wanted to show you is this would be a canyon. Like this is there's a canyon over here, but this is the up top of the Colorado River. It's actually the Yampa River, which is part of the Colorado, flows into the Green River, which then flows into the Colorado. But this is a canyon produced by this stream. You can kind of see it going through right here, and there's a tributary that comes down through here and goes into this stream right there. But this would be a gully, and then you get narrow valleys. Gorges are produced, and then you can get deep valleys, and then you end up with canyons, which are steep-walled. It's not really a canyon here, it's more of a valley, but steep-walled canyon like the Grand Canyon, which would be at the base of, or not the base of, but it would be a part of the Colorado River channel. So we have a process by which the stream downcuts and then laterally erodes as it's downcutting, because you have a floodplain and then the base level drops or something changes and you're cutting through. As you get this meandering back and forth, eventually you cut down into and make another floodplain underneath the one that was there before, and you produce these remnants of older higher elevation floodplains. But the way we use these, because they're remnants of older floodplains, we call this like the 10-year floodplain. And this would be the 100-year floodplain, and this would be the 1,000-year floodplain back here. And what we're talking about is basically we are going back in time, because these are remnants of older higher elevation floodplains, and if we fill them up, we're like pushing ourselves back to a stream that hasn't been seen in 100 years. So that would be the 100-year floodplain, and those are determined by these stream terraces. And then, as I alluded earlier, we have the Colorado River and these huge incised meanders, which are steep meandering canyons that are a result of down cutting, but not necessarily a lot of lateral cutting. And in this case, I mean, this is over many millions of years, obviously, but you can, if you get the right conditions, cut off this area right here, so you have an island, and you'll have a big oxbow lake. There's some very famous oxbows on the Colorado that are huge, and that's due to the same kind of activity that you have going on in normal meandering kind of stream activity, where eventually, if you get enough water, and right now the Colorado isn't really running all that strong because of the amount of water they remove for agriculture. That's almost dried up by the time it gets to California. But you get the idea that this still follows the same kind of evolution of streams, even though it's an incised meander. And Incise means to cut, because we have incisors, right, on the front of those teeth on the front are incisors, and what do we do with our incisors but cut? And that's basically, when we talk about incised meanders, it's just deep cuts, deep meandering canyons. Finally, we're going to talk about superimposed streams. Now, superimposed streams are kind of interesting because basically superimposed streams are following a specific channel, and then as they erode down, they run into a different material, but they still cut through it and produce what appears to be an odd structure where we have bedrock traveling one direction where you'd expect the stream to go north-south, but obviously the slope doesn't allow for that, and it's eroded down through many millions of years and will cut right through this harder rock material. And as it cuts down through that harder rock material, it'll produce a water gap, which is basically a canyon through a protrusion that's coming out from some bedded plain. And then we get a superposition that develops, and in a sense, basically the stream is superimposed over material that is resistant to erosion, and that's what you got going on here. I guess that was not well said, so let me restate that. Basically, a superimposed stream, think about it, it's basically a stream that has a specific channel, and as that channel erodes down, it may encounter underlying rock that isn't necessarily as easily eroded, but the stream keeps its course following pre-existing lithologies that are no longer there. That means rock types and things like that. And as these erodes downward into the underlying rock, it still follows its old stream channel, even though those rocks aren't as easily eroded. And they do affect the channel, but they still produce these very interesting open spots that seem to cut right through the mountains. The Green River is a good example of this, and you can look it up. Look up superimposed or superposition. I think superimposed. Sorry, superposition or superimposed is another way of superinduced is another way of saying it. But the superposed streams. Look up superposed stream and Green River, and you'll be able to see how it cut right through a mountain, basically. So in conclusion, we have the hydrosphere, which is the Earth's water. We have fluid flow. Almost all surface flow is turbulent, which is more capable of erosion and sediment transport. We have streams and rivers that possess potential and kinetic energy to accomplish their task of erosion and transport. The potential kinetic energy is dependent upon, of course, gradient velocity and discharge. But the sediment deposits of running water are called alluvium. You have alluvial fans if it's on the land, and deltas if it's in a body of water like a lake or the ocean. And then, of course, gradient velocity and discharge determines the deposition environment or what it looks like. And then stream valleys develop by a combination of these processes of downcutting, lateral, and headward erosion, stream piracy, mass wasting, and sheet wash. And that concludes this lecture.